Hello, morning. We had the midterm one on Monday, and I haven't yet got a chance to grade it. Probably, I'm not even sure Friday, but surely before, during the weekend, I should be able to. If I get a chance even before that. So I expect it around probably Saturday, sometime with the time to get it. But if I get a chance, because there are few number of students, there is a possibility that it might get graded fast. I grade the midterm, so it's any comments in general, any feedback that was it reasonable? Like whatever you expected or whatever I said is what happened, or thing you want to change, or at least you want to suggest something that should be changed. Okay, so let's see, we go the same pattern. So this is 1/4 of it every 3 to 4 weeks. We have an exam similarly. Okay. The next homework is on Wednesday, homework 4. And expect 2 or 3 more homeworks in between midterm 2. That's mark 4. I think this is the Friday before thanks. No, okay. It's spring, right? So this is a spring break. Friday before. So now that we have studied the electric force in some detail. So the basic idea is that whenever there is an electric charge, anything, any material, any object that has an electric charge participates or experiences a electric force. And then we go back to the old semester, the previous semester, and we try to do kinematics related to that. And we did 2 configurations. One was parallel plates and the other was point charges. Once we have the idea of electric force reasonably clear, we should be able to talk about electric energy. Any force has an associated energy to it. So we should be able to talk about electric energy. And more importantly, the electric potential, which is what we talk about whenever we see talk in terms of electric outlet. We say we want to plug it, plug our devices into that. So in preparation of that, to talk about electric circuits, we want to introduce the idea of electric potential, which is very closely related to energy. So that let me summarize. So we have electric charge. So we said it is charge Q. It comes in positive, negative, or 0. And then we talk about electric force. So that's F. And depending on whether it is a parallel plate or a point charges that is being discussed, this force could be said in terms of the electric field, or let me say this is the charge times the electric field, where the electric field is uniform. Electric field, let me say here, right? Electric field is uniform for parallel plates. That means you have two plates, one is positively charged, one is negatively charged, and we said there is an electric field which will be uniform in between the plates. And the other configuration we talked about is point charges, and in that case you have R hat times Q over R square, and that is a 4 pi epsilon KQ over R square, and this is for point charges. So that's the summary of whatever we have done. The basic idea is that we have introduced a force, depends on the charge Q. If there is no electric charge, no electric force, and we confined our discussion to two configurations, parallel plates and point charges, and this is the electric field, and if you multiply that with another charge Q, then you get the force. Let's review a little bit of what happens if you have a force. So this is review of work done. So one is work done by a force. So work done by a force. That's one point. Then we talk about potential energy. All this was covered in the last semester, but let's quickly review. That's potential energy. And the third is kinetic energy. And there's a connection between all the quantities. So basic idea is that Newton's law is mass times acceleration. Any mass, if you exert a force on it, or you don't have to exert one force, there could be many forces. That's F1 plus F2 plus so on. So the idea of Newton is that all the forces help you with the motion, and the mass, if you think of it as on the right hand side, it comes in the denominator. So the mass resists motion. If you're heavier, then it is harder to move things. So mass times acceleration is equal to the sum of forces. That's Newton's law. If you think in terms of energy, we can say the motion itself is talked in terms of kinetic energy. Kinetic means motion, like energy associated with motion. So change in kinetic energy is equal to the work done by each of those forces. That's W1, that's W2, so on. Right. And that introduces the idea of what is the work done by a force and what is the kinetic energy related to motion. So the work done by a force think of it as always the work done by a force. That takes away the confusion or any conceptual issue with the colloquial usage of the work done. When we say that I have done so much work, it's me who is doing the work. But now think of it as a work done by a force. Whatever is the source of the force, that particular force does the work, and then there is no issue with the colloquial usage that we have for work itself. So work done is by a force is given by the dot product of the force itself times a displacement. How much does a mass move? So this is the force itself. That's force. And this is the displacement. And this, of course, is the work done by the force. This is a multiplication of two vectors, and this involves the magnitude of the force. When I do not write the vector sign, it means it's the magnitude without the direction, times the magnitude of the displacement, how far have you gone as far as magnitude goes, and the angle between these two quantities, the force and the displacement. So for example, if you're exerting this is your force F and that's your displacement. Think of it as you're trying to move something on the ground, but you're not exerting the force in the direction of the displacement you want. Instead, you're exerting in some other direction, then all the force is not helping with the displacement. If you break this into two components, right, so there's a horizontal component and a vertical component. The vertical component doesn't help you with motion. It is a horizontal component that is helping you with the motion, and the angle between them is that constant. So it is a horizontal component. It's F cosine theta. That's F cosine theta times the distance, and that's what is the work done. So, so how much energy does it gain? So that's the way you want to interpret this. The work done is a measure of how much energy has the force put into the mass. Whatever energy shows up has to show up as kinetic energy. If there is only one force, then there is only one work. So if you change this, then you have to change the kinetic energy. It's another way of saying that if there is a force, there will be motion. In terms of energy, if there is a force, then there will be a work done by the force, and that will show up as change in kinetic energy. If the mass was at rest, it will start moving. If it was already moving and the force was resisting it, then it can also reduce its kinetic energy. So K here, kinetic energy K, is equal to half mv squared. So, and always you go from initial point to the final point. So the velocities, if the velocity changes, kinetic energy changes. So that was a very quick review. And I should also say potential energy, right? Potential energy is the work done by a force. So potential energy, U, or change in the potential energy, is the negative amount of the work done by a force. So then you would say, why talk about potential energy at all if it is so directly related? This exists only, so only if the work done is independent of the path taken. And it turns out that there are very few forces that actually satisfy this condition that should be independent of the path that it takes. One of them that you studied last semester was the gravitational force. If you have anything moving in gravity, then you can associate a potential energy associated with gravity. You call it the gravitational potential energy. All through most of what you study in the early part of physics, you only see about 2 or 3 forces which are actually having a potential energy associated with it. One is gravity. The second is electrostatics that you study here. And the third is the spring force. Whenever you have a spring, you extend it, it comes back. There is a potential energy stored in the spring. That's the third situation you consider. And there is no other situation you will see in the early part of physics. Later, if you do advanced physics, there is the strong force and the weak force where you can associate an energy to them. So now that I mentioned that there is an electric force has a potential energy associated with it, so we can talk about work done. Negative of that will be the potential energy, and that energy can be associated with motion, and you can calculate the change in kinetic energy associated with that. So that will be our goal here. So let's talk about how we can think of potential energy. Before that, let's see the work done by the electric force. So let's have a scenario where we have electric field pointing downwards. And I take this example because this is very much like gravity, right? If you have an electric field lines that pointing downwards, and it acts like gravity when you put a charge in. So this is electric field E. It's pointing downward, and let's say this is equal to 5 point. Let's say the direction is. The direction is minus j hat. Magnitude, let's say, is 5.0 into 10 raised to 4 Newton per coulomb. So that's your electric field. Whenever you have electric field lines given to you, that means that if you have a positive charge in here, it will go in the direction of the electric field. So think of it as a flow. A positive charge flows along the lines of the electric field. In fact, the force experienced by this charge Q, so that's charge Q, is Q times the electric field itself, right? And we have shown this as lines which are equidistant, electric field lines. If they are equidistant, that means it is uniform electric field. It doesn't matter whether you're here, here, or here, everywhere, it's the same electric field, exactly like gravity on the surface of Earth, gravitational field, or G that we say 9.8 meters per second, that doesn't change so much around. If you have a negative charge instead, so if you have to put a negative charge, you can again ask what happens to that negative charge. It goes in the opposite direction. In that sense, it falls upward, right? When you have a mass in gravity, it falls downward, right? There is no other, you don't see a scenario where you drop something and it goes up. But here we have two scenarios. If you have a positive charge, it will fall down in the sense that it goes along the electric field. And if you have a negative charge, it goes up. So you have two situations here. Let's have the first situation. And let's start from point A, and let's go along a straight line up to point B. And from that point, I'll go horizontally to point C. And we want to talk about, first, let's say A to B. What is the work done in going from point A to point B? That's what the question we can ask. Notice, I'm talking about work done from going from point A to point B. I can reach point B from point A in many ways. That's only one possibility, right? That's a one path. I could have gone like this. I could have gone like that. I can go all the way, go there and come back. So there are infinite ways of starting from point A and reaching B. And this is a very specific path I have taken. So let's calculate this anyway. Since I've given the path, we'll address the path independence very soon. But the work done from point A to point B is the force times the displacement. So let's say this is height h. So that's your h, and let's say this is about 15 centimeters. So the work done is the force acting on this charge. So we have a positive charge here times the displacement. So we need to have a force dotted with the displacement. Let's say this is d. Force acting on this positive charge is downward. So let's say it is Q times the electric field. Q is the magnitude of the charge. So let's say this is magnitude times the electric field, and it has a direction pointing downward. So that's minus J. Right? So that's minus J. That's a direction. That's your force. Force is Q whatever is the charge Q here, maybe I should point out, so that's Q, let's say, is plus 1.0 into 10 raised to minus 6 coulomb, micro coulomb. This could have been negative. If this was negative, then I have to put that negative sign here. So the force will be in the upward direction. So that will be plus G. Right? Whether it's positive or negative, think about the force and do that accordingly. The displacement, I said, is we are going straight up. So straight up would be plus G times, let's say, H. So that's your height, H. So that's your force, that's your displacement, and I've written it in such a way that the directions come next to each other so that I can take the dot product immediately. So the direction J hat dotted with J hat, that is cosine of the angle between these two directions. Now, two directions both up, or you can think of it as force is up, the displacement is also up. What's the angle between them? That's 0. That's cosine of 0. 0 is the angle between the force and the displacement. Cosine of 0 is 1. So that's equal to 1. So that's your magnitude of force, magnitude of displacement, and cosine of the angle, which in this case I've shown it as the direction of the two vectors. This comes out to be, that is a minus sign, and that is a charge Q, which is 1.0 into 10 raised to minus 6. Electric field is negative sign I've already taken care of. That's 5.0 into 10 raised to 4. Height is 15 centimeters, that's 0.15. It is a negative quantity, notice, and otherwise it is, that is a 10 raised to minus 2, and 5 into 15 is 75, so that's minus 0.75. The units of work is newtons times meter, but that's such a common factor or common unit, we will associate joules with that, or that is a vocabulary for Newton times meter, that is joules. So that's the amount of energy, or that's the amount of work that is done by the force when a charge plus Q has to move from this point to that point. A positive charge tries to go down, so you have to exert that force in the upward direction. That's your work done, and then we have to talk about what is the potential energy. But before that, let's talk about what is the work done in going from point B to point C. This time, the force itself is F, and the displacement D times the cosine of the angle between them. This is the angle between the displacement and the force, and you again see what is happening. The force is always Q times E. It's in the direction of the electric field. Electric field is always pointing downward, a positive charge is always down. But the displacement D is in this direction now. Earlier, the displacement was in the opposite direction of the force. Now the displacement is to the right. So this is the displacement B to C. But the force is acting perpendicular to it. Whenever the force is perpendicular to the displacement, that means that the force is not helping you with the displacement at all. In fact, the angle between them is 90 degrees. And that's 90 degrees. and cosine of 90 is 0. So it doesn't matter what this force is, what this displacement is, this will be 0. So there is no work done by the electric fields when it goes from here to there. And you could have gone however far you want. You can keep moving around, but there is no work done by the electric force in that motion. It is equivalent to saying if you are on this floor and you walk 10 miles up and down on this floor and then ask what is the work done by the gravitational force. There is no work done by gravitational force because you did not go up or down. Do not confuse with what is the work done by you. Your muscles have done work, you have eaten, you have spent a lot of energy for that, but that's not what we are discussing. We are talking about what's the work done by the gravitational force when you're moving horizontally. And since you're not moving against the gravitational force, it does not do any work. It is the work done by gravity. In this case, you're talking about the work done by the electric force. Electric force is pointing down. If you're moving horizontally, it doesn't matter. It doesn't do any work on you. So it is very free as far as electric force goes. You can go from here to there and no cost at no cost in energy. The same idea you can now use if there is no energy needed to go horizontally. You will notice that whenever you want, if you want to reach point C, I can go up here, no cost in energy when I'm going horizontally. And I go here, then I go up, go down here, then I go up here and go like this. That's another way of going from point A to C. And you will notice there is no energy here. No energy spent in this, no energy spent in this, no energy spent in this part, and all the vertical parts add up to actually going from A to B. So whether you're going from A to C in this part or you go straight up and then go right, it is the same amount because all the horizontal segments did not contribute to any work done. It is only the vertical segments, and those vertical segments will always add up to be the same. This piece, that is, so let's say this is 5 centimeters, 5 centimeters, 2 centimeters, and 3 centimeters. They will add up all the time to be the same because electric field is constant. In fact, you could have changed this to any path you want like this. And then you would say, oh, is that the same? Again, break it up. Break this path into small vertical and horizontal components, and always only the vertical components add up. Horizontal components will always be 0 because the electric force is perpendicular to that. Using this simple thought process, mainly that there is no work done when you're moving perpendicular to the force, you can argue that whichever path I take to reach point C is the same, which is the same as going from A to B, which means that I can go up here and no spending energy, and when I'm coming down, it's the same amount of energy I lose. So if I make a full circuit, the work done is always 0, right? Because of whatever energy you spent in going up, you will pull it. When you come back, you're spending it back. And that's the statement that the work done is independent of the path. Or I said earlier also, if you're going from A to C, whether I go this way or this way, it doesn't matter. And electric force in this manner is such a force which does not care for which path you're taking. And then there is a big advantage. If it does not depend on the path, then it just means that it only depends on point A and point C. It only depends on the final minus initial. Not many forces do that, where the motion depends only on the final and initial point. It is like saying, if you're in the context of gravity, the way to say it is that if you're going from here to the third floor or the fourth floor in Neckars, but meanwhile, during the trip, you go all the way to another city and come back and then ask, what is the work done by the gravitational force, it's the same amount, whether you take the straight path up to the Earth or you go all the way to another city or for that matter, another galaxy and come back. Whatever energy, potential energy or gravitational potential energy you spend in going one way, you will spend it coming back because it is independent of the path taken. And the same thing for the electric force also. It is the final minus initial that matters. And then you say that, oh, if that is the case, why talk about the work done at all? Because work done is one number, let's say going from A to B. Since it is independent of the path, I can associate an energy at the final point and the initial point. Both points have some importance because it's independent of the path. So I say this is U of B. So that's called a potential energy at point B minus the potential energy at point A. Don't worry about the path, only the final minus initial. And for conventional reasons, this has a negative sign in front. So it is a negative of this. So this is called the change in potential energy, which is negative of the change in U. So earlier we said here that the work done by all the forces is equal to change in kinetic energy. That means that if there is an electric force alone, the change in kinetic energy is equal to, suppose there is only electric force and the work done by the electric force is change in potential energy. That's on the right side. I said that's a convention, it is a convention, but most probably it was done so that this is such a fundamental quantity, you put it to the left hand side and so that you can talk in terms of change in kinetic plus potential energy. So change in kinetic energy plus the change in potential energy due to electric potential energy is exactly zero if there are no other forces acting on. And this is the quantity we want to talk about as to what is U. So we said whenever there is a work done, there is a potential energy. So what exactly is the potential energy for the electric force? So let's figure that out. We almost have it here. So this is for parallel plates, so electric potential energy. We said the work done by the electric force is Q times the electric field, right, dotted with the distance d. Let's say the height h is in the direction of the electric field itself. So we have, this is the parallel plate configuration we are having in mind, and that's your electric field. Whenever we have this scenario, we say this is positive charges and that's negative charges, and somewhere we say that's your height h. So you go from point A to point B, and the change in potential energy is equal to, this is Q times E times D, that is this electric field that's going down. So let's say if you were to go from this point to that point, so before that I can say that a positive charge, if it was here, I have to, if I want to push it up, I have to exert some force there. So there is higher energy here. This is higher energy for positive charge. For positive charge. And this is lower energy. So in that sense, so you would say this is Q times E times H, and we do not worry about, so the height is always a vertical height. That's H. You should compare this with gravity. If this was a gravitational force, you would say it is mgh. If you remember from your old semester, the potential energy associated with gravity is a force mg times h. Now it is a force, electric force times height, exactly the same idea. And it's always a vertical height. So this is important that I've taken care of this dot product. It takes care of only the vertical component. So that's vertical height. Even if you're going this way, going from this way, this point to that point, it's only the vertical height that matters. The horizontal doesn't come into picture at all. That's yeah, and maybe I should say delta H, right? Just so that because it's a change in energy. That's Q times E times delta H. That's the basic idea. Energy is force times distance, and it is the vertical height in the sense it's in the direction of the electric field. If I had turned this plate around, then you wanted to get the component of the distance that is along the electric field. That's important. So that's your electric potential energy. And it's also good to talk about what about point charges? We have to do that also. We have to multiply by a distance. So let's talk about that. So these are potential electric potential energy. For point charges. Let me draw a configuration first. That's your positive charge, and the electric field lines for this look like this, radially going outward. That's your electric field lines. What's the formula here? So now if you have another positive charge here, it tends to go out, right? If you have a positive charge here, it tends to fall down in the direction of the electric field. Here, it tends to go in this direction. So that means the electric force will push it that way. Where is the potential energy high? Wherever the electric field originates. So if you're going in the opposite direction of the electric field, it will be high in potential energy. Whenever it is closer, notice what is happening here. If I were to go from this point A to point B here, and it doesn't matter how I go from point A to point B, but to make it simple, let's say I go along on the surface of a sphere that is equidistant from the positive charge. And then again, let me ask, what is the work done during this process? The force is radially outward between the positive charge and this, the force is always radially outward. That's your force. At every point, wherever you are. So at this point A, this positive charge tends to push the other positive charge. As I move to the right along this curve, since I'm going perpendicular to the force, again, the work done is 0. So that's the analog of the situation where if I'm going horizontally here, it does not do any work. So along this path, so the work done is 0 on a sphere of fixed radius. So what is the potential energy going to be? So at this point, there is a distance r, and at this point, there is another distance r. And it is only the distance from the origin that matters. So you would define your potential energy as the force, which is 1 over r squared, multiply it by a distance, the r goes away, and the potential energy, U, will be equal. It's not a vector, because the vector goes away when you take the work done, and the potential energy comes out to be 1 over 4 pi epsilon naught Q1 Q2 over the distance between the two charges. Notice the force had r square in it, and the potential energy only has 1 r in it. So there is only one power. Basically, the force multiplied by distance, one of the distance went away in that sense. So dimensionally speaking, it is only 1 over r. There has no direction because it's a scalar quantity, and the potential energy is higher for between two positive charges. It is higher as you get closer and closer. What is the change in potential energy between points A and B? So now let me change the points A and B. So let's say this is point A, and that's point B, and that's here. So that's another circle. This is another circle. So the change in potential energy would be equal to U of B minus U of A. So this is B to A. So I'm going from A to B. It depends on the path. They go from point A to point B, and that's equal. So this is K, right? So this is K Q1 Q2 over the distance from the center, that's RB, and minus of K times Q1 times Q2 divided by R of A. That's your change in potential energy. Once we have these numbers, we can actually calculate this and proceed from there, but we will come back and do those kind of problems next time. For now, we have introduced the potential energy, and we will exactly in the same spirit do potential energy per unit charge, and then proceed from there. We'll stop here, and thank you. I set this up all completely, but I never changed the camera.